61A, Lecture 17, Q&A.
Okay, so I think the question is about the relationship between yield from and how that's essentially unpacking a for loop.
Yeah, the yield from is just a convenience. There's no real reason why it's in the language, but it is. It takes two lines and turns them into one. So going back to the example from lecture, which was trying to yield all the prefixes of some string s, if s, meaning f, s is not the empty string, it said yield from prefixes of everything in s up to the last letter. And then yield s itself, because s is a prefix of s, depending on how you define prefix, but that's a fine way to think about it. And then we need to call this on something like, I don't know, dogs. So that should get dog and do and d. Notice that this result is not a list. If we'd want to do something with it, we'd have to pass this in or call next on it or something like that. I believe the doc test just called list on it, which is basically get all the contents. And we got all this stuff. Yield from can always be replaced with a for statement that says the following. For some new variable in the thing that we're yielding from, yield x. So that's what yield from does, is it goes through all the elements of some iterable and yields each of them.
So it's just a syntactic shortcut. That's all. It's a bit essentially saying, look, this is what you will find often, not just in Python, but in a lot of programming languages, that things that are routinely coded by hand are eventually incorporated into the language with a little bit of shortcut. It's abstracting out some complexity here.
Yeah, exactly. Once you know what it means, it's a little bit easier to read. Before you know what it means, then it's harder to read, right?
Right. And there's a question in the chat, do we always need a yield statement after a yield from? And the answer is no. We could have just commented out that yield and it just wouldn't have returned the list as part of the prefix. I mean, that would have been incorrect in terms of the functionality of prefixes, but you can just have essentially a yield from is a whole bunch of yields. And so in this example, if we had commented out yield s, it would have worked fine. It would have just given the wrong answer.
Yeah, good question. The question is, for the correct implementation here, what is prefixes s of all of s without the last letter? This is an iterator over all of the prefixes of this. So if this were dogs, this would be dog. And prefixes of dog would be all three, d, do, and dog. So yeah, it's not just like the first prefix, it's all of them. And that's why what we're doing is we're yielding the d, the do, the dog, and finally we're yielding the dogs.
Hey, John, there's a question in the chat. Sorry to interrupt. And why, when you ran, we get comments about yield s, and when you ran it, it returned an empty list.
Yeah, great question. So the question was, if we comment this out, what's the behavior? And we showed you right here. It ends up yielding nothing. Why is that? Well, we've written something that just yields the prefixes for the smaller version. So if this is dogs, we're yielding whatever we get by calling prefixes on dog, which in turn would yield whatever we get for calling prefixes on do, which would return whatever we get for calling prefixes on d, which would return nothing. We've reached, which would return the result of calling prefixes on the empty string, and that would yield nothing. So the base case here is like, if there's no letters, then there's no yield. Therefore, we're not producing anything. And since we don't produce anything in the base case, and all this ever says is yield whatever the next recursive call would yield, we end up not yielding anything at all. So in general, if you ever have a function where you yield from an empty list, that's not going to yield anything at all. Yeah, good question. So if an iterator is not a list, what is it? There are lots of different kinds of iterators. So you know it more by its behavior than it's like what it's constituted of. An iterator is something that you can call next on and get more elements. In the case of a list, the iterator for a list is more than just a list. It's kind of a reference to the list along with a position in that list that tells you where you are. So that if you call the next thing, the iterator advances, meaning that if you called next again, you'd get something else than you did the first time. So in that sense, it has different behavior than a list because it's both a list and like a marker for where you are. But list iterators are not the only kind of iterators. You could have an iterator through the labels in a tree. You could have an iterator through the prefixes in a string. You could have an iterator kind of through anything. And it's just a description of something that lets you go through multiple elements in some order by calling next on the iterator and getting the next value. And you can do that over and over again. So it's quite an abstract thing as opposed to feeling quite as concrete as, for example, a list.
Well, the question about when should you use the built-in Python functions is an interesting one. I imagine if you ask different people, you'll get different answers. So I'm going to answer and we'll see what John has to say. So my view is languages are not static and they change. And so this functionality comes in and out. So for example, if I want to write some Python code and put it on my website, and I happen to be using the latest, greatest version of Python, and I grab some function that just got introduced, I don't know if somebody using an earlier version of Python will be able to run my code. And that's not great. I don't like that. I like for my code to be standalone and not rely on somebody having just upgraded. So now you could say, look, this requires Python 3 point whatever, and that's the way it is. So I prefer to write code on my own, but there are limits to that. I'm not going to go re-implement some gnarly, like if I wanted to use an iterator, I wouldn't implement that myself. But I like to implement my own code in part to make it compatible, and also because I just like to know what my code is doing. I always get a little worried when we use code that's all canned up and we don't really understand it. So I like to do things, I tend to do things more on my own. But if you are doing rapid prototyping and you just want to get something built, sure, using all the built-in functions is great. It saves you from writing a lot of code and doing a lot of debugging.
Yeah, I think that's a great answer. I think everyone who's building software has come to a point that they've written a ton of code and then realized, oh, this is just like a special case of some general thing that's built in. I've basically just like rewritten all the mechanics of a dictionary or something like that, when in fact I could have just like used the one that's built in and it would have been one line. And that's okay. Happens to all of us. And is the version that you wrote better or the built-in one better? It depends. It depends on how it's going to be used. Like Hani said, especially if something's just recently been introduced, then it's probably worth avoiding it for a while if you want to be kind of compatible with everybody else. But using the built-in functionality means that your program might get better without you having to do anything at all. Like if you're implementing your own system for time zones, this is fine, except that what if some island somewhere changes their time zone? This happened in the 90s. Christmas Island decided to change its time zone. Like you have to go in and update that. Whereas if you use the built-in system for handling time zones, then it would just get fixed for you in the next version of Python. So I think there are generally advantages to using the built-in stuff or relying on open source libraries, whether it's part of the language or it's like part of some community development, rather than just like redoing everything yourself for the long term. But like if you're just getting something running, like it's totally fine to just rewrite stuff yourself and ignore yield from and nothing bad happens. I'm going to go back and quickly answer your other question that I know you know the answer, but just for posterity's sake, the question was, what happens if you invert the order of yield S versus yield from S? Like, what's the difference? We can just quickly look at that and see that if the yield S comes afterwards, that means S, which was originally dogs, is the last thing in the list. If instead we had yielded that first and then yielded all the prefixes, then we'd see everything in the opposite order. So really, Python's going to go through and do these things in the order that you write them. And that will have an impact on exactly what happens. One more thing I wanted to say about this example is that what if we didn't know about yield? Like, what if we were just in the business of building lists? Could we still get this behavior? And the answer is yes. It would look something like this. We start with a list. We go through, and instead of yielding, we would append to that list. And then for every x in the list of prefixes, I think we would append that x. And then when we were all done, we would return that result. And in fact, in the base case, we'd want to return an empty list. So in either case, I think we want to return the result. And here we get something that kind of does the same thing. And if we inverted the order, then we'd get it in the other direction, going from D to dogs instead of from dogs to D. And a lot of code looks like this and kind of avoids this notion of yielding in general. And that's fine. There are sometimes efficiency benefits to yielding. There are sometimes some interesting concurrency benefits to yielding. So it is something that does get used more and more as people advance in their sophistication of programming. But it's not like you really need it in order to get stuff done in the first place. You could just explicitly build the list instead of yielding it piece by piece. Okay, so the question was in the countdown example, why is it the case that you have to yield from countdown k minus 1? This was if k is greater than 0. And then we yielded k. How come we couldn't just yield countdown k minus 1? Well, let's just try it both ways, see what we get. And then I think we'll understand. If I list out the contents of the iterator that I get from counting down from 5, I'll get 1, 2, 3, 4, 5. Oh, I think I was supposed to count down. Yeah. Woohoo! Okay. If instead I yield this, what I'm yielding is an iterator rather than a number. So what I'm going to get in the contents of my list is not a bunch of numbers, but instead one number, the 5 that I yielded, and this generator object. And what's this generator object? Well, if I get this result and I get result 1, here's this generator object. This is something I can get the next thing from. And so I can get that 4. It's buried in there somewhere. It just took an awful lot more work to get it than in the other version where I just ended up with a bunch of numbers.
So essentially the from is unpacking that list that is now sort of stored up in the generator, because what is yield from? It's just a for loop that iterates through the result. Yeah, and if you don't iterate through it, all you do is you have that sort of core generator. But the result, as John just said, is still there. It's just sort of that lazy evaluation that you have to now unpack it.
Yeah, good question. So the question is about this example, and why is it the case that when you get the length of the result of listing out the contents of an iterator twice, you get a different thing each time. First time you got 3 things, next time you got 0 things. This isn't something having to do with len. This is having to do with how list interacts with an iterator. When you call list on an iterator, you end up building a list of all the contents of that iterator, but the iterator is used up as a side effect of calling list on it. So if I have an iterator over these values, I can get one thing out of it, but then if I get another thing, I get a different thing. List is kind of like calling next over and over again and putting all the results in a list. So as soon as you call list on T, you're going to get everything that's left over in the iterator that hasn't been used up or returned already. So we've already seen the 1, we've seen the 2. Therefore, calling list on T will just show us the 3. And now T is used up. I can't get the next thing in T because we're already at the end. And so if I try to list everything that's left in T, I'll get an empty list. So your version was start with this, get all the contents of that, which is a list containing 1, 2, and 3. If I do this, I'm changing t. This is every time you get elements from an iterator, you're changing that iterator, which means you can't really use it again. So if you get the len of this, you get 3, you get the len of this, you get 0.
So think of these iterators as one-use disposable operators. Once you've gone through the list, either next, 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 or the list of it is you're essentially enumerating the list, it's gone, right? So, and by the way, you could have implemented this yourself. You could have written a function that every time you access an element, the next element, you delete that element from the list. That's essentially what's going on here, yeah? And so once you, it's a funny thing about iterators, by the way, is that once you look at the list, it's sort of like, what is it? It's like Snapchat, right? The image comes in, you look at it, and then it vanishes, it's gone. Yeah?
That is beautiful, yeah.
God, you got to be impressed by somebody my age making a Snapchat reference. That's you know, you got to get a little credit for that.
Perfect Snapchat analogy. Great question. Yes, this is a form of mutation. So this is why we teach iterators right after we talk about mutable values, is that all iterators are mutable. They always change whenever you do anything with them, meaning we call next on them. So the question is there like real applications of yield as opposed to just returning? I see it a lot. It often appears in cases where your program is interacting with something else. So there are lots of cases where you want to return a list of things, right? Instead of just returning a single value. But sometimes that list of things that you want to do something with isn't all there at the same time. So classic examples are you're like reading contents from the web, and you want to start doing stuff with each element of the, you know, like each page in a website. You want to be printing out its like a title or something like that. You'd write a function that gets all the pages in a website and returns them so that some other function can print out their title. Well, it takes time to get all the elements of all the pages in a website, because there's like network traffic and you might have to discover where they are. And so that's a classic case where you would be yielding each page as it becomes available. And that means that whatever's printing out the title can start printing stuff right away as soon as the page is available, instead of having to build a list of all the pages in some website, which might be huge, before you ever kind of start work on anything else. So yeah, there are other cases in which there's this kind of like pipeline of information flow where stuff sort of is becoming available incrementally and you want to yield it as soon as it's available. That's where it's used a lot.
I think that's exactly right. I was thinking of the example. You can tell the difference in John and my research. John does natural language processing, so he talks about text. I do images and video. So my example is we take a video and we have to decompress the video to do an analysis of it. Decompression of a video is very, very slow. But I want to start processing as soon as I get the first few frames. So as I'm decompressing the video, I'm shoving frames out the other end, and then I have an algorithm that's doing some analysis and it's shoving it out. So when, I think it's exactly right, is when you have these different pieces in a data flow, but the processing is not exactly the same. So maybe you have some slow steps, some fast steps. And I don't want to sit here waiting for this really slow process, because I can start working as soon as I get the data. And so that with return, you couldn't do that, right? Return says, I'm going to hand you back all of this data when I'm done. The yield can do it incrementally.
The next question was, is a generator always an iterator, but an iterator is not always a generator? Iterators are not always generators. There's lots of different kinds of iterators. And generator is just a particular type of iterator. And what makes it a generator is that it came from a function that yields, as opposed to being from a list or something like that. So iterators describe anything that you can iterate over, whether it's the elements of a list or the yielded values from a generator function or anything else, whereas generators are more specific. But the way you use a generator is the same as how you use an iterator. It's just talking about where it came from. The next question was about the summer 2020 midterm, question 2. Okay, so this says schedule takes a galaxy, which is a string, and then there's some number that you want to sum to, and some max digit that you're allowed to use. And so a galaxy looks like something that's a bunch of digits, maybe with some question marks. For example, here's some digits and some question marks. And then there's a completion of a galaxy, which is a string full of just digits, where we've replaced each question mark with a digit, and the total sum of the whole thing is supposed to be this value sum to. So here's a legal way of doing it, which is that you could fill in this question mark with 0. Well, this has to stay a 2. This question mark was 0, this question mark was 0, this has to stay a 1, this has to stay a 1, and this could be anything we want, but all the digits, including the ones that are provided and the ones that we added, have to sum up to 5. So here's all the ways of doing it. Okay. Let's take a look. Seems like we'll do some recursion. We have a helper, which has galaxy. The fact that there's a galaxy here and a galaxy here means that maybe we'll be changing this along the way, like filling in digits, for example. Here we have a sum so far, which could tell us whether we've reached the sum that we're trying to eventually achieve. And the index, I guess, means that we're going to walk through here, element by element. Okay, so we'll call schedule helper on the original galaxy. The sum so far, I think, is 0. We haven't done anything yet. And we'll start at the beginning, and we'll see what we do. If it's the case that we're done, then we're going to return a list containing galaxy. Okay, that's good. But this means that the galaxy that gets passed in here has to have all the question marks filled in if we're going to be returning it. So we know we're going to be kind of filling in things as we go. If it's the case that maybe we've reached a sum that's too big, then we have a problem. So I think there's probably some base case like sum so far is greater than sum to, then we have a problem. There might be some other base cases that we have to think about as well. I'm not sure what's going on here yet. We'll think about that later. Here's the kind of main recursive loop, which is that we build a list. We go through every x in something, probably the digits from 0 to 9 or something like that. And we fill in a question mark. That seems like what modified galaxy is going to be all about. So I kind of feel like this is going to be the case where there's no question mark, and this is going to be the case where there is a question mark, and then you have to like try all the possibilities. So it might be something like if galaxy at index does not equal a question mark, then I think we have to just use that first value. So we'll call schedule helper on exactly the same galaxy we had before. The sum is going to change. We have the old sum plus whatever the first element of galaxy is, or the current element of galaxy is. And what else? Let's advance the index so we keep moving. What if there's a question mark? So here, this is, in fact, I'm just going to rewrite it. Elif galaxy index equals question mark. And I think this will do the same thing, right? Oh, wrong way. We're going to find all the different ways of doing this. Go through the digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to build a new string, which is galaxy up to but not including the index plus a stringed version of x plus the rest of galaxy after the index. That might work. So let's just like look at what this does for an example before we go on. It would be nice to know that it works. So if I have something like 2, 3 question mark, 5, 6, and I have an x which equals 4, is it the case that if index equals 2 and galaxy equals this thing, that I get what I want when I evaluate this expression? It does. So we basically just replace the question mark with a 4 there in this long line. So what do we do? Well, we have to get some more answers in there. I'm going to recursively call schedule helper on this new modified galaxy and a new sum so far, because now we've got an x in there and we're moving forward. And we do this for all the index. Like, why is it the case that I called schedule helper here? This is where I'm going to fill in all the other question marks that are later on and make sure that I got the sum right. All right, now I think we need to get this base case of when we have found a fully complete galaxy. So this would be like if index equals the len of galaxy, then we've gotten to the end. And if galaxies, well, okay, how do we do this? Let's make sure we got the right sum. Sum so far equals sum 2. That might do the trick. Then maybe we're done. Nope.
Index out of range.
Or index greater than or equal to the len of the galaxy. So if you kind of like get to the end and you don't have a sum that's big enough, then I guess you need to stop. What on earth? Sorry, Zoom is in the way. I can't even see what broke.
Oh, I don't think you're supposed to use.
Oh, parts up to size max digit.
Yeah.
You can't always go to 10.
Yeah.
Should probably read the question first. Okay, now it works. So what got us here? Well, we kind of kept track of what information we needed to maintain along the way. And there were like some pretty good clues in the question of what to do based on the name, sum 2 and sum so far. It took a minute to kind of think through the base cases. And I think we could have figured this out without running the code, just by kind of like considering different cases, reading the question carefully. But since we had it all set up, we just ran the doc test instead to get a clue about whether we had done it right or not. During the Q&A, I said we could do this with yield instead of building a list, but we never actually did that. So let's do it. We're going to return a list of the results of everything that scheduler helper yields, and then we can worry about yielding. So here we would yield just galaxy. That's equivalent to returning a list of galaxy. Here we just wouldn't do anything. One way to stop a function is to write return, but it would also be fine just to kind of do nothing here. Just don't yield anything. And what about here? Well, schedule helper is going to yield a whole bunch of different values. So this would have to be replaced with the yield from. And here we could get around building up a list and just say that every time we call schedule helper, we'll yield from that. So what happens when we run this? We get the same result. Great question. So if you have a for statement or for loop, is that the same as creating an iterator and then calling next on it repeatedly? Yes, the behavior is identical. I think there are cases in which Python tries to like find a faster way to do it. Like if you iterate over a range, maybe it's doing something fancy underneath. I don't know. But from your programmer's perspective, the behavior is identical to create an iterator out of this thing that you're running the for loop over, and then call next repeatedly, binding the name x to the next value each time. Yeah, good question. Is there any way to reset an iterator once you've gone through the elements, or do you just have to make a new one? And the answer is you just have to make a new one. There are the reason for this is that it might be that you're trying to write a program where you're kind of forgetting the past, because maybe the stuff that you've iterated over is so big, it's like whole video files, that you can't store them all in memory at once. So this idea of like resetting would require you to remember everything you had seen before, and that's exactly what you might be trying to avoid with an iterator. So it's up to you to write your own program about remembering where you were. I think there might be some like built-in stuff in the Python standard library to remember an iterator and kind of cycle through it, but I don't know exactly what it looks like. The next question was, is there a relationship between yield from and recursive functions? Like, do yield from always have to be recursive?
I don't think of it as recursive. I think of it as iterative, because you're just unpacking a for loop. John?
Yeah, that's right. So I don't think yield from has to be recursive or anything like that. You know, the simplest possible yield from would be like yield from all the elements of this list. And there's no recursion there. And it works just fine. So you have to start with a list, 1, 2, 3. But then if you call f on that and you get that result, this is a generator object where you'll get the 1, the 2, and then the 3. It happens to be that you can mix together recursion and yielding if the goal of your recursion is to build up a sequence of things, which is not totally unusual. You know, our first examples of recursion were like count the number of ways that you could partition up a number using parts up to size m. And then we just did a homework problem, which was actually list out all the ways. And so, you know, it's the same basic recursive structure in both cases, except for counting, you just return a number. Whereas if you're listing out all the possibilities, then you have to either return a list or you have to yield. Yeah, good question. So can yield be used within a list comprehension or inside of another larger expression? The answer is no. And this is also true of return and assignment statements and def statements. There's a lot of things that can't be embedded inside of a larger expression because they're not expressions themselves. They're statements, and so they have to kind of just like show up on their own line. So you never have like return x for x in some list, because return x is not the kind of thing that you can embed inside of a larger expression. And the same is true with yield. You can't have that there either. Yeah, good question. So is there a way to kind of do two things here in a list comprehension? And the answer is you only get space to put one expression, but that expression could be a compound expression. So, you know, one expression is the number 2, but another expression is the list 1, 2. Because this whole thing, the list 1, 2, is actually just one expression that's got parts within it. You could try to get each part to do something. It is legal in Python to say, first I want to get the result of printing 1, and then I want to get the result of printing 2, and use that to fill in this blank. And now I've kind of like done two different things, but I've done it by calling a function, which is something you're allowed to embed inside a larger expression, as opposed to writing down a statement like print or yield, or sorry, like a return or yield or def, where you're not allowed to embed that inside something larger. Yeah, okay, so the question is, how would it be that like new stuff appears in an iterator as you're reading from it? This was an example from earlier in the Q&A, and what might it look like? If you have something that's like read pages from a website, well, every website has like a root page. So maybe we should call this root. It would be something like, I don't know, google.com, or how about the New York Times? You would have to have some function that reads that, right? And so you'd like call that on the root. and get this page. And you'd want to yield this page. And that means that like whoever called read pages can immediately start acting on this right after this is done. But then I think you'd want to go through for get all the links in this page. And you'd want to yield from the result of reading all the pages from that other page that you got. So how is it that we're like getting new stuff along the way? Well, you're kind of not. In some sense, all of the data that you will ever process is known, is defined when you call read pages the first time. It's whatever's at www.newyorktimes.com and everything that it links to. But actually writing out that list of everything linked to from the New York Times will take a really long time. And so there's a lot of this result that we haven't discovered. We immediately kind of yield the front page, and that means that something could print the title right away as soon as this line is executed. But we haven't really found all the other pages yet. So they're there, but our program doesn't know about them.
Okay, that makes sense.
Cool. All right, thanks, folks. It's been a pleasure. Talk to you soon.